Thanks for being here. It is a very nice afternoon for me to be here because talking to an audience of highly qualified young researchers is always a considerable satisfaction, professional satisfaction in an academic career like mine is. So thank you for being here. And it is also particularly exciting to know that for those of you who are going to attend the summer school, ACM Summer School next week, this week may represent some turning point in your scientific career because you are going to learn some hints or may simply increase your passion. And this is an additional professional satisfaction for me to be here and for meeting you during next week. So my background is in electronic engineering. I'm a professor at the University of Rome, Sapienza University of Rome, but I am a visiting researcher here at BSc in the European Processor Initiative. We are going to focus a bit more into the accelerator design. You have heard a very interesting and comprehensive presentation from Andrea about the overall architecture. Now we are just looking into a piece of that. The contributors to this material are Adrian Cristal, Luca Benini, and also I'm not reading here. I'm sorry, Professor Labarta, that is going to talk in a few minutes. We're going to look a bit at the accelerator roadmap and the two parts of the accelerator architecture: the vector processor and the neural stencil processor. So, just a little recall, this is the overall architecture of the so-called GPP, General Purpose Processor, that Andrea has introduced. You have several tiles inside. Among these tiles, one of them, the green one here, is the so-called EPAC, that is a European Processor Accelerator. Very fantasy name. Okay. So we are talking about that. We're going to talk about this. And someone asked about the foundries. I'm going to tell something about that in a few seconds. How does this falls into the EPI roadmap in the timeline? You see, these are the steps that are expected to regulate the development of this project. We are going to, the first target, we are going to tape out a general purpose chip, the first revision of that. And as you see here, it is going to contain CPU general purpose CPU tiles based on ARM technology, ARM instruction set, and the accelerator tile that is based on RISC-V. We are going to get back to RISC-V after a few slides. So it is an heterogeneous architecture, also talking about the instruction set. But in addition to that, more or less in the same period, that is end of 2020, start of 2021, we are going to tape out an accelerator test chip that is only devoted to the RISC-V accelerator. This is, let's say, more for demonstration purposes, for showing that the capabilities of the accelerator as it is, not inserted necessarily into the overall general purpose processor system. And we are going to tape out that more or less in the same period. This one is going to be 7 nanometer FinFET technology, and this is going to be less aggressive technology, 22 nanometer FDSOI. So now I will focus about this, because the next step are later on in the timeline. By the end of 2022, the second revision of the general purpose processor, the GPP, is expected to tape out. And this will be the real product, let's say, that is going to be, it's expected to be ready to be integrated in a supercomputing system. Before we go on talking about the hardware microarchitecture, I want to spend a few words about the vision that BSc has developed concerning the design of the accelerator. And this comes from a discussion that I had with Professor Jesus Labarta that you will hear after my presentation. So if we look at the exascale future, so the supercomputing in the exascale era, being capable of executing 10 power 18 operations per second. What is the scheme that we expect to reach? If we look at what is the present scenario, we have some established vendors of technology, basically computer system vendors. The paradigm seems to be very well defined. Basically, the GPU world. Accelerators in the supercomputing systems are now based essentially on GPUs. Yet, by the way, the people that are giving us the money, that are the politicians in Brussels, they basically follow the established vendors. However, what we are worried about is that programmers are allowed to survive the exascale transition. So if we go on in this direction, having flat paradigm, homogeneous parallelism, everything is CUDA, or maybe some other similar programming paradigm, the explosion of parallelism may be intractable from the programmer's point of view. So there is a possibility that we have to turn the vision of the future sooner or later and go to something that is more structured. This is actually the concepts that you see here are, let's say, the basic pillars of the design of the accelerator that we are developing here. So targeting a hierarchical parallelism and heterogeneous architecture, decoupled architectures, I'm going to talk about that, heavily pipelining because of, especially in the vector acceleration, exploiting locality because the memory bandwidth is limited, and this is done especially through the use of long vectors, as we're going to see in a few slides. Abstracting the view of the architecture to the programmer, this is mainly obtained by a very careful design of the runtime system that is not something that I'm working on, but it is an essential part of the system design. Malleability, meaning targeting the capability of adapting the system to change in the workload, dynamically changing the workload. This is something that is relatively frequent in everyday operation of the supercomputing system. And from the technology point of view, let's say what I'm more involved in, the circuit level, the RTL implementation, targeting low voltage synthesis, low voltage libraries, and for the fabrication point of view, chiplet technology, which is the base of the general purpose chip implementation. So this is not working. Okay. We are we're trying to move the future, the vision of the future, in that direction by developing this innovative design. A few words about the instruction set. You heard this word, RISC-V. Yes, we are targeting RISC-V in the accelerator part because RISC-V represents several advantages that I'm going to tell you now. We are not targeting ARM for one main reason, because ARM is not European anymore, and the accelerator, therefore, is based on RISC-V. And you may ask, okay, why don't you base everything on RISC-V? The reason is that there is no presently available high-performance general-purpose microprocessor based on RISC-V in the market, and it is not, let's say, in the possibilities of the consortium to design one in a reasonable amount of time. Not to mention that the ecosystem on which that is based on ARM is a very strong driver for maintaining some part of the development based on ARM. So it is okay for now to base the development of a general purpose computation subsystem on ARM instruction set and go into RISC-V, so to innovation for the rest of the architecture, which is basically the accelerator subsystems. Why RISC-V? Because RISC-V has no legacy. It allows you more freedom. Of course, you don't have to pay licenses, and this is especially interesting for the industries. RISC-V can be extended. This is very important. And in particular, the standard vector extension is extremely interesting for the European processor design. RISC-V is contributed by a committee of worldwide experts. And in one sense, they are doing jobs for us, which is very interesting in one sense. So of course, PSC is contributing to that. The limitations are that many people contribution is also implying many features that may be not of interest to everyone. There are some points that are not very interesting for us, even in the vector extension, for example. And especially, okay, the political issue question. RISC-V is governed by a foundation that is based in the USA, but this is not the context to talk about that. Anyway, that issue is going to be solved, like what I can tell you. Yes.
And just a small detail.
Yeah.
The foundation is currently established in Canada, not in
Yeah. Yes. You are right.
And in North America, but different administration.
That's right. Okay, it is no secret that they are planning to move to Europe. As I know, and because they told us directly, and so in order to avoid any kind of problem on that. But anyway, this is not the context. We are talking about technical things here. Of course, there is the ecosystem problem. RISC-V is starting now. However, the ecosystem is a big problem for example, in the consumer market, where you have a huge software ecosystem. In supercomputing systems, it is not, anyway, a negligible problem, but not of the same size. So, a few words about RISC-V vector extensions. How many of you are familiar with vector processors here? Okay, I'm probably talking to the other part. RISC-V vector extension specifies 32 logical vectors, vector registers. Each of them has a length that is machine dependent. And we have several interesting features in this instruction set. Let's say a lot of operations, orthogonality between scalar and vector operations. More or less, you have the same operations available for vectors and scalar data. You have the several possibilities of using vector scalar, and vector immediate instructions. You have masking, that is predication, having the possibility of doing or not doing the operation on specific elements of the vectors, based on a mask that is a bit mask contained in a register. Loads and all the possible vector loads, classical vector loads and stores that you find in vector architectures, that is strided, non-strided, gather and scatters, and other variations. And also reduction instructions. For example, summing up all the elements of a vector or finding the maximum and the minimum and so on. You have some vector control registers, control and status registers. V-type specifies, in particular, the width of the single element of the vectors, and the type also, maybe floating point or integer. Vector length is the vector length that you target in your operation is another control and status register. V started is the number of elements to start with after an interrupt. And another vector FCSR that is related to rounding modes, okay? We don't have the time to go into detail here, and also I have to say I am a microarchitecture guy, so I don't have a full view of the instruction set issues. So some examples of vector instructions for those that are not familiar with them. For example, addition, you have the addition of two vector registers, element by element, and you store back the result into a third vector registers. When I say vector register, you can imagine, for example, a vector of 256 elements, each of them being a double precision floating point number, 64 bits. The operation can be masked. This VM is the mask. So you can add or perform the addition or not to some elements according to a previous condition. This is a control instruction that is setting the V-type register. In particular, it sets the length of the vectors of the vector operations to be used and the size of the elements, the V-type. These are two examples of load and stores operations. You load one vector starting from a certain address in the memory into the vector register file. Of course, I've not said it, but the machine architecture is supposed to be a register file-based machine. So, having said this, we can talk about the hardware design. This is a sketch of the general purpose chip that is going to be taped out by the end of next year. It is targeting 7 nanometer chiplet technology. You heard that there are basically three vendors, three technology providers for this. Samsung, Intel, and TSMC. It is not difficult to to guess which is the one that we are going to address. This one is going to be on 22FDX technology from Global Foundries, European foundry in this case. As it was said before, there is no realistic possibility of having a European foundry supporting 7 nanometer fabrication within the time frame of the EPI project. So we don't have the possibility of doing this part, fabricating this part in Europe. Okay. This is the test chip that is incorporating only accelerator tile. That is based on RISC-V instruction set. You see internally, I'm going to detail now, but the structure is based on a scalar core controlling vector lanes. This is the vector processor part, and you have multiple of them. And also specialized units that are called the STX. They are more targeting rather AI applications, basically neural network training. And we are going to detail them in a few seconds. I don't know if this number can be said, but anyway, you see there, so there is no confidentiality anymore. So let's take a look at the microarchitecture of this API accelerator. The microarchitecture of the accelerator tile is based as you see, on a local NOC, local network on chip. You have L2 caches here, and you have the processing units on the bottom side. And you have bridges to the network on chip that is interfacing to the general purpose processor array, the big processor array. On this part here, you have the vector processors. Here you see 3 of them. Actually, we are targeting 8. And the internal of that is based on a scalar core. This is a RISC-V scalar core controlling vector lanes, which are the functional units equipped with the portions of vector register files operating directly on the vector data. Of course, we also have a lane interconnect, and we're working a lot on that because we need to move vector elements also between among the lanes, which is a relatively complex problem, technically speaking. On the other side, here you see the specialized unit. Specialized unit, as I told you, mainly target training algorithm for deep neural networks. And they are based on scratchpad memories, a local scratchpad memory, of course, interfaced again with the memory subsystem through the NOC. This is another RISC-V core. It is let's say, smaller and simpler core than this one. And the specialized data path is inside these blocks. Again, you have multiple of them. Up to 8 can be controlled by a single RISC-V core in each of these specialized units. So you can see there is a kind of a hierarchy inside the architecture. Okay, this is the first time that this picture is publicly shown. It is a detailed, simplified, very simplified detail of the microarchitecture of a vector lane. Here you see, by the way, I'm talking about this guy here, one of this, okay? So you see here, we have several register file banks. For those of you who are interested in implementation, there is a debate about implementing these with SRAM macros or with standard cell-based register file banks. This depends on the size. Okay, it is a discussion that we may have if you want. We are still exploring this part. But the RTL design of all these things is ready and working anyway. So you have these register file banks, and you have you see 3 buffers here. Actually, the buffers are all double buffers. There is a reason for that. It is not now the case for discussing that. This buffer here, A, B, and C, contains the input operands for the functional unit that is represented by this part on this side that is actually doing the real operation. So basically, this is a floating point unit, in particularly capable of doing fused multiply-add operations. That's the reason why there are 3. In case you have fused multiply-add, you do A times B plus C. So you have 3 operands. Then you have a write-back buffer here on the top, and you have load buffer and store buffer. We can take a look at how an instruction like this is executed on this scheme. By the way, this is very, let's say, yes, it's very close to the Cray-style supercomputer architecture that some of you may have studied. So assume that we have to do this addition V1 plus V2, vector 1 plus vector 2, and put the results in vector 0, okay? This is the pseudocode that is executing the same thing. This is what you would write in a scalar processor, in a sequential program to be executed on a scalar processor if you do that with C language. So you have the color coding is that V1 and V2 are the green and the blue. These are the input operands. They are distributed through the banks of the register file. So for example, this is vector element 1, element 2, element 3, element 4, and so on. And then you start again, maybe 10, 11, 12, and so on. And the same for the green one. We start by reading n elements of the green vector in a single cycle on the buffer A. This is a single cycle access. And in the next clock cycle, we read n elements of the other vector, the blue one. And then we have this queue of input operands ready to be executed by the pipeline functional unit. So we go on consuming the elements that are contained into the input buffers, and accordingly we go on producing the results. By the way, one comment about that, you see that we have used just one port per bank, one port per register file. This is important because augmenting the number of ports makes your register file slower. After we have the first element ready here, it starts filling the write-back buffer. When the write-back buffer is full, in a single cycle, we write down the elements that we have produced into the destination locations of the register file. And so we can go on like this. In this way, we have 100% utilization of the functional unit. When, of course, after an initial startup time. You may say, okay, why this particular organization? Because, for example, take a look at this intermediate point. While we were still producing some result here, the register file is idle, meaning that we are not reading or writing anything there. And so we can use this time slot, for example, for loading data coming from memory, while we are performing a vector arithmetic operation. And similarly, we can interleave operations by proper design of the timing of the microarchitecture. So this is just to give you the concept of that, okay? Coming to the STX specialized units, so we are talking about, sorry, it is a bit long to go back, but anyway. We are talking about this, okay? This block here. It is the one that is devoted to neural network training. Okay, this one is, you will see very clearly, it is much more special purpose microarchitecture. It is based on a published design, so you will see much more details if you want on that. It is a floating point coprocessor. The heart of the microarchitecture is the capability of performing 32-bit floating point multiply and accumulation, in particularly in a single cycle. And also having the hardware support for loops and address generation. So it is much more dedicated architecture. As I said before, up to 8 STX units can be controlled by a single RISC-V core. And yes, floating point, 32-bit floating point is the preferred choice for training neural networks. So this is the very basic unit inside the STX. Very, very, very small subsystem here. It is the floating point multiply accumulating unit. An interesting thing of this microarchitecture is that, okay, it performs multiplication and accumulation in one cycle. This is thanks to the fact that you use carry-save arithmetic inside. And you can do so relatively quickly. And the interesting part is that there is a conversion here from floating point to a 300-bit fixed point format. And you do all the arithmetic in fixed point internally. And then you convert back into floating point. Why is it like that? This is a design that was developed by ETH Zurich. You can look at the publications that they have written on that, and there is a quite interesting work to study. Of course, it would be, by the way, it would be a totally different story to think something like that for 64-bit double precision floating point. So this is a very specialized solution. This one is the heart. If you look a bit at higher level, this one becomes this, the basic functional unit, and you have several components around. All those components you see are devoted to, let's say, support some part of the typical operations that are used in neural network training. For example, the rectified linear unit is a possibility after multiply accumulation, is a possibility to be applied to the output. The unit operates like a streaming processor. So it receives streams of data here, performs the multiply accumulation and possibly other operations, and then produces an output. This is not a RISC-V processor. This is programmed by means of specialized commands, very, let's say, little number of possible commands that are fed into this queue here. Several features of these. You can also have the possibility of finding maximum and minimum. This is for supporting the max pool operations, again related to neural networks. Finding the argmax and argmin, so the point of maximum and minimum of the function. The output can be masked to 0 and 1. All of this can be useful when implementing the training algorithms of typical CNN. And it is programmed by commands here. But this is not the end of the story. You have support, as I told you, for nested loops in hardware. You have counters. When this counters ends its number of iterations, it triggers the next one, and so on. So you have the possibility of implementing up to 5 nested loops in hardware in this microarchitecture. And you have these address generation units, which are basically addition units, which compose the addresses for the memory by adding up a base, the possible stride, and other addressing modes that are supported by the microarchitecture. You have 3 of them because you have 2 operands and 1 result to address to the memory. If you put all together, this is the floating point multiply accumulate. This is the overall floating point unit, including the rectified linear unit, the comparator, and others. Here you have the address generation unit with the counters. Here you have the controller. This is basically a complex state machine that decodes the commands coming from this interface here. And these commands are written as memory mapped commands from the RISC-V, the external RISC-V processor. So basically, the RISC-V processor writes through the, as if it was executing store operations into the memory, writes a specialized control words that are controlling the operations of the microarchitecture. This is the general scheme. Yes, okay. You have queues for the addresses, 2 input queues for the operands, 1 queues for the data output. And this is called the NTX or STX. NTX is the old name, let's say, because it was subsequently modified to support stencil algorithms. Again, sorry. Look at this symbol here. So all this thing is the STX or NTX. The big picture is that many of those can be controlled by the RISC-V, by one RISC-V core here. And this is the specialized unit that is integrated into the accelerator tile of the GPP. Okay, so you have on this side here, you have the interconnect to the NOC that we looked at the very beginning of this story. If we, okay, this is the internal, it is called here TCDMM, tightly coupled distributed memory. Anyway, it is a kind of a scratchpad memory that that is put there to exploit locality. We can conclude with a very small example. If you try to write a sequential RISC-V code that performs a dot product, multiply accumulation over 1024 elements, you come up executing more than 5,000 instructions, and the code is there. For those who knows RISC-V, you may go through the details of that. If you execute with STX support, you see that the commands becomes actually store operation, this is store word, into the specialized memory locations that are mapped, that maps the commands of the STX unit. And so overall, you need to execute the 10 of those store instructions in order to program your STX unit, and then the operation, the unit operates for 124 cycles. That is a considerable performance gain with respect to the original one. So, if you have any question, we can go on with more details, or we can pass to the next lecture. Thank you very much. Oh, sorry, I didn't realize. Thank you.
As I understand, the accelerator, the memory bandwidth for the accelerator is also important. So
memory bandwidth.
Yes. So
yeah, yes.
You have the solution for that?
The solution, okay, of course, the memory bandwidth has been, let's say, sized according to available technology. It is, I don't like to say this, but we are not allowed to talk about numbers of this kind. Anyway, the solution for memory bandwidth is locality. Both the vector acceleration and the STX acceleration are based on local memory. On the vector side, you have the register file, the vector register file, and on the other side, you have scratchpad memories. Both structures actually have the role of exploiting locality in order to avoid having to write very often to or reading very often to the memory. And the longest vectors you have, our machine, I can tell you, targets a minimum of 256 elements, double precision floating point, which is considered a long vector size in the present technology scenario. The longer vector you have, depending on the applications, of course, the more locality you can exploit. I am not a software guy, so I cannot tell you the application that can actually fit to this scheme, but that is let's say the microarchitecture solution that we are looking at.
And how about the memory space? Like you use the same memory space with the
The L2, no, It is a bit long to go back to the initial one. Anyway, the L2 cache that you see on the accelerator tile is shared among the vector processor and the STX specialized units. In this moment, I don't think that the general purpose processor share the same, sorry, I don't think that the general purpose processor memory space is coherent with the accelerator memory space. We don't support global coherency. I have to say I don't work at that level of the architecture, but this is the information I have. So this cache L2 cache subsystem is actually shared between the cores that you see here, and the L1 cache here belongs only to this Scalar core.